let's go ahead with the seminar. At this occasion, I will present our next speaker. Is Professor José Baêta. He's professor of the Mechanical Engineering Department of the Universidade Federal de Minas Gerais in Brazil. He's director of the Mobility Technology Center and researcher in the area of propulsion and biofuels. Currently coordinates 4 research projects in the area of innovations in new propulsion systems and new fuels with the participation of large companies in the automotive sector. Professor Baêta is High Productivity Scholarship holder of the National Scientific and Technological Council of Brazil, with more than 120 published scientific articles and 2 international patents used by large industries. Let's give Professor Baêta a warm welcome with a big round of applause.
So first of all, thank you, Professor Herman, for your kind presentation. And it's a pleasure for me to be here and have this opportunity to talk to you all and exchange knowledge with all of you, okay? So it's a pleasure for me. My presentation goes through the study of fuel conversion efficiency in a single-cylinder research engine with gasohol and ethanol mixed with hydrogen obtained via catalytic reforming. First of all, it's important to contextualize this. So gasohol, because in Brazil, the gasoline is mixed with ethanol, okay, anhydrous ethanol, in the proportion of 27% of anhydrous ethanol with our gasoline, right? And currently, our government is changing this with 30% of ethanol now, okay? So this is normal in Brazil. Since we are a tropical, let's say, country, so we can live with a high percentage of ethanol in our gasoline. And our ethanol is a hydrate ethanol. So we have there 6% of water content in our ethanol, right? This is important to explain. Okay, and why we are conducting this R&D with some fossil fuels and biofuels together, because it's important to understand for us when we mix this with hydrogen, which are the advantages and the drawbacks we can get using biofuel like ethanol, which is highly used in Brazil, and the gasohol with hydrogen. And what's the right proportion of hydrogen that can be used if you are aiming at the fuel conversion efficiency? This is another question. This is very important as well. Okay, it's important to explain as well that our, let's say, our ethanol there and our hydrogen is still very costly in Brazil. Okay, so we need to let's say the primary source that you have to get this hydrogen is very important to make this really affordable and cost effectively, right? So let me try to go. It's not changing. Oh, I go here. No. This one. No. Let me see if I point there. Oh, okay. Better this way. Okay, now it's okay. So just a quick summary. So I'm just going to present to you a big picture, overview of our R&D, let's say, laboratory. I think it's important to understand what we are really doing there. And then we go through the R&D main objective of this presentation, the methodology applied, the results obtained, the conclusion, and wrap up, okay? Right. So, our university, we have 80,000 square meters, okay, of area, and this is really a big engineering school, and have lots of, let's say, courses that, a variety of courses in the engineering there. So we have around 300 professors, 150 employees, 7,000 students, 11 undergraduate courses, 11 graduate programs as well. Okay, we are located there. Professor Herman had the opportunity to pay a visit there and know everything. And this is an overview of our, let's say, capabilities. So we have a fuel and combustion lab, engine R&D lab, vehicle R&D lab, turbochargers characterization lab, vehicle design and simulation lab, electronics lab, flight simulation lab, more for the aeronautics, hybrid and electric vehicle lab, wind tunnel lab, velocimetry lab, thermometry lab, engine combustion analysis lab, CF&D lab, and biofuels lab. So we produce our own biofuels when you need to, let's say, understand different, let's say, types of fuels as well. So there we have 3 bench dynamometers, okay, for multi-cylinder engines, 1 dedicated for a single-cylinder research engine that could operate in the thermodynamic way or also with a transparent kit, right? And different control systems as well. The combustion analysis is something really important to us. So normally we use the equipment from AVL in Graz, and we can track all the combustion process and understand it very well, the mixture formation, the combustion, and so forth. Well, so now let's go through this presentation, specific presentation. So our R&D main objective is really to try to understand which would be the best fuel conversion efficiency using gasohol and ethanol mixed with hydrogen. So it's the first step of our R&D. But now we've been invited by Professor Herman to go further than this and push this to the ammonia and hydrogen mixture as well. So we believe that could be really something promising for years to come, right? So this is our single-cylinder engine, okay? So it's an engine that we can operate, as I said, thermodynamically, or even with let's say, the transparent kit. And we can use different techniques like PIV, particle image velocimetry with a transparent kit, or also a phaser Doppler anemometry, depending on what you want, you know. So shadow imaging, mixed scattering, or so forth. Well, for this specific research, we've been operating with 14:1 compression ratio, okay? And the reason for this is really to, let's say, try to push the maximum engine efficiency that you can reach using the hydrogen. Before starting explaining about the hydrogen, it's important to understand that the use of hydrogen sometimes is tricky because let's say the activation energy of hydrogen is really high, so we can face knock very easily, let's say this way. So we need to be careful about the engine, let's say, calibration and how to use it properly. So just to give an example, hydrogen normally burns 4 times faster than gasoline, right? So the turbulence, the internal turbulence of the combustion chamber could not be the same as you have with the gasoline or ethanol or some, let's say, liquid fuels that we are used to dealing with. So this is something we need to be careful when we are going to explore the maximum efficiency of something with hydrogen. It's common. If you go for a pure hydrogen, you need to, let's say, to redesign your engine entirely to do with this. One of the problems that we have working with the pure hydrogen is that normally we have a concentration of hydrogen in the crankcase of the engine. And this could be really explosive. So we need to be careful about this. You need to have a specific system to drain the hydrogen from the crankcase to make it really safe. Okay, this is very important to to bear in mind before getting started. And our test cell needs to be completely, let's say, redesigned to work with hydrogen in a safe way as well, right? But if you use just a few amount of hydrogen, if not necessarily more than 15 or 20%, we can live with the current, let's say, test cell that you already have. So this is important to be clarified. Well, this is our, let's say, our installation there. So we work with a single cylinder engine, firstly, in a thermodynamic way. And we have our ECU. So we have different types of ECU there. So we can program the ECU. We can calibrate everything by ourselves without the need of any other company to be involved. This is important to be clarified as well. And in this specific research, our intention is not to produce, to use the pure hydrogen mixed with gasohol and ethanol, but we produce let's say, the hydrogen by means of catalytic reforming in our exhaust, right? Injecting some amount of ethanol there, right? And then we can separate the hydrogen and burn this hydrogen inside of the combustion chamber again, okay? This is, let's say, in terms of costs, is much more affordable. And the amount of hydrogen needed for a high fuel conversion efficiency, we're going to see later on, okay? But just to explain very quickly what's the arrangement we have and how does it work, right? And then later, if you have any question, you can just let me know. Well, this is just one screen about our indicated pressure system there from AVL, the INDI model, okay, the INDICON software. And there we can monitor not only this screen, we have much more than this, but other sheets as well. But this is the main parameters that must be monitored. So the mass burn fraction, okay, is important mainly for developed combustion from 10 to 9%, let's say, mass burn fraction. And we also monitor the beginning of the combustion and the end of the combustion and compare also the mass burn fraction from 10% to 50% and from 50% to 9%, just to see how the combustion and where we have, let's say, the middle of this process, how it's going to be, and if you are working at MBT, at maximum brake torque or not, right? And we also had a histogram to monitor knock occurrence there, based on the frequency of the combustion and the intensity of the knock when we reach this point, right? So this is important to understand. Well, and here, let's see if I can make this work now. I don't know how to make this. I have an animation here. I need to go there, right? I cannot see the presentation here, but let's see. Let me see if I can find it. Oh. I think it's in the PDF format. It's not going to work. Not in PPT. It's PDF. Don't worry, man, but let me explain here, no problem. We have there in blue, okay? We can see there the signal from the coil, okay, the ignition coil. So we can see by means on the crank angle there, we can see when we just load the coil, and then when we just stop loading, we have the spark generating. In the let's say green signal there, we can see our direct injection of ethanol there, right? Just one injection. We can have a split injection in some, let's say, break points as well. And there's a specific one we calibrated only with a one injection. Okay, we have also the rate of heat release there, the first on the top, the first, let's say, red curve. And on the bottom, we have here the pressure trace, the in-cylinder pressure trace, right? So what we need to explain it when we have this in animation. We can see the combustion there on the top right-hand side, right? And you can also see here the crank angle, let's say the crankshaft angle changing, the IMAP, the Pmax, and the other parameters concerning the combustion process, right? So this is normally we use this during our R&D to monitor and understand correctly what's going on inside. So we can not only, let's say, look at the parameters that we get from the software, but can also see the combustion inside when it's necessary. So we do not use only the transparent engine, but with the thermodynamic engine, we have the visioscope, we have the endoscope that you can look inside and see the combustions taking place, right? This is important. Well, this is, let me go for the results now, just to explain to you. So see here, you can see the indicated specific fuel consumption, okay? And the mixing percentage of the hydrogen with the ethanol there. So what we can see when we achieve around 9.27% of hydrogen, we do not have more benefits using, let's say, increasing the percentage of hydrogen in the ethanol, okay, mixture. So this is important. This is the first thing that we need to understand. So you do not need a huge amount of hydrogen to achieve the maximum, let's say, fuel conversion efficiency. Obviously, if you change the, let me say, the turbulence inside of the engine, decreasing this, we can get more benefits from the hydrogen as well. So we believe that because we know the properties of hydrogen and how we can get the most, let's say, fuel conversion efficiency from hydrogen. But for the current engine, as we've been using here, I think you do not need more than 10%, right? This is important to be understood. Well, here we show, let's say, with ethanol and hydrogen, another thing that is very important. Our, let's say, previous belief was that we're going to speed up the combustion and then we're going to get the higher fuel conversion efficiency. It's not so simple like that, right? Sometimes we do not speed up a lot, let's say, the combustion process, but have another benefits from the, let's say, the energy that comes from the hydrogen and the combustion as well. So there you can see the spark timing for the ethanol. Since we have a very, let's say, charge cooling capacity, we do not need to change the ignition timing, okay, or reduce this because of knock occurrence or something like this. It does not occur with the ethanol because since we have a high latent heat of vaporization, really high, and the high cooling capacity that I think is more important than the octane number at that time, we can really, let's say, get rid of any out ignition that can be, let's say, becomes a knock event, right? So this is important as well. So it's just to give an example. This we are operating at 3-bar IMAP, indicated mean effective pressure, and 2,500 RPM, right? So it's a common, let's say, load and speed used in a current engine. So that's the reason, because you consider that point. We checked much more than this, but we do not have time to show all these results, so we're gonna just concentrate on the main results we have. Well, here looking into the cumulative rate of heat release, right? Comparing pure ethanol with ethanol with 10% hydrogen, which we found as a good point, right? We can see that you can really speed up the combustion, right? We can speed up, but at the end of the combustion, it's get a bit slower. If you see that at the top of the curve, you can see that, right, as well. So this is normal, okay? This is normal, and mainly because you are exchanging heat with the walls on the combustion, inside of the combustion chamber, and with let's say the cooling liquid for the refrigeration of the engine as well. Well, here just to show you, okay, the pressure curve, and the pressure curve you can see that this is higher, and we have a more, let's say, work available from the engine, and this way we can make this more efficient as well if you're just using this type of mix. So just to show you what we got as a basic curve using, let's say, 10% of hydrogen with ethanol, right? Right. So, talking about the exhaust temperature, obviously, when the conversion efficiency increase, the fuel conversion efficiency increase, the temperature of the exhaust goes down, right? And we see there the temperature that we could reach with 10% of hydrogen. This is good, right? One of the problems with hydrogen is normally the temperature of the flame. Right, this is a diabatic temperature, flame temperature is something really important, mainly because of the NOx formation. So when you decrease the temperature in the exhaust and the combustion, let's say, becomes more efficient, this is good. But you need to be careful about the diabatic flame temperature. Well, talking a bit now about gasohol. As I said, our gasohol is a gasoline with this, in this case, 27% of anhydrous ethanol, right? And its content. And as you see, up to 15% of hydrogen, we, let's say, decreased the indicated specific fuel consumption, which means with fossil fuels, with the gasoline, a mixture with ethanol, where you have let's say, different types of hydrocarbons and so forth, we have a different behavior. You're going to see that the ignition time must change because of knock occurrence as well. And this sometimes is not so, let's say, we do not face a huge advantage as normally we can face using the ethanol, for example. So here you can see that the ignition time or spark time is changing, okay, depending on the amount of hydrogen that we are using at the very same, let's say, IMAP in the very same RPM speed, right? So as we see here, sometimes we need to retard the ignition timing, okay, to avoid some, let's say, combustion issues. This is important to be clarified as well. Well, and sometimes when you are doing this, we see that the mixture of hydrogen with gasoline does not produce a huge advantage in the cumulative rate of heat release, as you can see, compared with our E27. We call E27 because of the 27% of anhydrous ethanol mixed with gasoline there. But it's not the same as a pure ethanol mixed with 6% of water, right? So this is important to be also shown. And here is a point that you can see the pressure trace, the pressure curve. Also, you have also a drawback sometimes operating in gasohol. There are some breakpoints that we can have a good gain operating with, let's say, gasohol mixed with hydrogen. And there are some conditions there is no advantage operating with hydrogen mixed with gasohol, right? So this is something we are studying. We are looking at this, but normally is a combustion issues caused by let's say, the low latent heat of vaporization of gasoline, which could be good for, let's say, cold start and warm up the engine, but during the, let's say, the operation with, let's say, in the normal conditions, not so good. Well, regarding the temperature, we face it in this condition an increase as well sometimes, comparing let's say, the gasohol with the gasohol mixed with hydrogen. So this data up to here is important just to show you that going for the biofuel like ethanol could be much more promising than gasoline, right? This is important. It does not mean that you cannot have any gain with gasoline. This is not true. As I said, depending on the calibration map area that you are operating. And just a conclusion about that, very quick conclusion is that our ethanol fuel economy is okay, operating with hydrogen. The combustion development is okay as well. And the exhaust temperature decreased as well. Okay, and by means of our study on the numerical simulation, we could also see and measure by our emission devices that we have benefits in the emissions as well. Not shown here so far, because I thought about 30 minutes maximum, so I just reduced the presentation. But we can also have a very good, let's say, promising data regarding emission. And for the gasoline, the fuel economy, in some points okay, some points not so okay. Combustion development, we faced some drawbacks, and the exhaust temperature sometimes as well. So I got a very, really polemic break point just to show that, right? So this is what I have to present to you very quickly, and my contact is here. If somebody wants to contact me later, I'll be really happy to exchange some thoughts and talk, right? Thank you once more, and I'm open to questions.
Thank you, Professor Baêta, for your presentation. Yeah. I will open a question for you. Why do you choose this specific combination engine operating conditions? So, are you testing preliminary research? You say preliminary research. Are you thinking to try to test actual conditions of engines in the market, for example, for vehicles?
It's a very good question. First of all, this data makes part of a doctorate program of a specific student there that worked with us. She finished the doctorate, let's say, course as well, but it's important to understand that our first station is to compare the hydrogen mixed with a fossil fuel, very used in Brazil, like gasohol and the ethanol, right? Just to see and if there is an advantage going for a biofuel instead of fossil fuel in terms of fuel conversion efficiency, firstly, okay? Then we go for other aspects, but this is the first point. Regarding this specific break point, we found a condition where we had some issues, some drawbacks with gasoline as well. So this is important to show the difference, because there are some breakpoints that gasoline and ethanol are close to each other, and we do not have lots of different, right? Obviously, a more complete study is now ongoing because we are, let's say, controlling the turbulence inside of the single-cylinder engine and just changing this to have a better understanding about this combustion with hydrogen, trying to get the most from the hydrogen, right? And still comparing gasohol with ethanol, right? So this is our intention. So first test is just to understand for a standard condition, right? What's really happened with ethanol and gasoline. But the second round now is to go further than this and try to understand the combustion process. And in parallel, in our CFD lab, we are conducting lots of, let's say, simulations to just, let's say, vary the turbulence generation, right? And then we can really understand the contribution or the drawback from some different conditions. And the kinetic mechanisms have been studied as well to understand more about this, all right, and the species and so forth. So we have a deep research on this right now. And one important thing is when you told me about this promising R&D with ammonia and hydrogen, I think that could be really something powerful. Just to give an example, I think this is a bit polemic, but it's important to clarify that in our lab, we've been studying a lot about hybridization, and about electrification. We have a specific paper studying, let's say, the energy matrix of the entire world to understand what's going on. And when you start just calculating things, this is electrification does not work properly, in my opinion, right? We did not have raw materials enough for a large electrification. And sometimes electrification does not mean decarbonization. It depends on the primary source of this electricity, right? So I've been dealing with lots of politicians talking about electrification as a solution for everything, And we, as a researcher there, we do not believe that. So it depends. We are not advocating, let's say, in favor of combustion or something like that. No, we do not have any preference. We're just studying, let's say, the technology behind and to understand how it could be really promising for the entire society. You know what I mean? So we need to change completely the material of the batteries. We need to change completely the way to recharge batteries. You need to make this much more, let's say, much safer than it is regarding fire and other things that we've been, let's say, facing around the world. So this is our belief. So this is the reason because we are insisting, let's say, investigating here combustion with, let's say, advanced combustion systems. You know that you've been there and you've seen there that we are working with HCCI, the homogeneous charge compression ignition. And at low loads, where normally the SI, the spark ignition engine, is really low efficient, we could increase more than 20% the fuel conversion efficiency working with HCCI for a hybrid system, for instance. Imagine an engine running with ethanol, with HCCI, an electric engine here, you know, for the propulsion, but you use let's say, a biofuel in a high efficient way, you know, to really make this really promising and attractive, not only for the government, but for the consumers, you know, for the clients. This is the most important thing, because who's going to pay the bill? That's the question. You know what I mean?
Interesting, your point of view. So, could you give us a detail regarding the cracking system? So you are talking
what?
about cracking system because you mentioned that you use the exhaust system, the exhaust gases to produce hydrogen
Yes.
from ethanol. So
Yes.
how it works?
You can do this with, let's say, SI engine, or even with, let's say, CI engine, compression ignition engine. Doesn't matter. Okay, we have a specific reformer. This is a catalytic reforming process. You inject the ethanol, and this is really complex. We have 5, let's say, chemical professors working with us there. Okay, for this, to optimize this reforming system, but since we have a hydrogen and obviously an oxygen inside of our ethanol, as well, for sure. So we can separate this hydrogen and just, let's say, direct this hydrogen for the combustion chamber again. This is the cheapest way I know to generate hydrogen and make it work for an engine, since you do not have so much hydrogen to make this engine really efficient. For the time being, we concluded that. But as I told you, since we are changing the mixture preparation, let's say our turbulence generation system, we are working with flaps and metal sheets to change completely the in-cylinder motion, or to reduce sometimes for quiescent combustion, to understand really if I can increase the amount of hydrogen. You know what I mean? So, and we are also simulating this numerically to see if you can go further than we've, let's say, arrived, so we got so far. So it's something that it's under R&D, under investigation, right? But it is important to clarify that, let's say, this is not, let's say, easy to optimize, okay? We are underway, we are doing that.
Thank you, Professor.
Yeah.
Christine, you have any question, something?
So you say that in fact you don't separate H2, oxygen, CO1, CO2, right? So the reformer, you put everything in the equation.
Yes, I would say that let me say that the hydrogen that we get there is not 100% pure, right? This is, we have some concentration of other gases in a small quantity, but we also have other gases, so it's not a pure hydrogen. But we also use the pure hydrogen from the tank to compare. So, but it works perfectly. So we do not have, let's say, a need to spend more money to get a pure hydrogen. This is what we understood so far.
And it is 10% of energy share or 10% volume?
Sorry?
10%
In mass,
mass.
yes. Yes, so I don't know if you could see here, but we have let's say, a specific system to measure in a mass space the amount of let's say, of gases produced from the reforming to be injected another time inside the combustion chamber. But we have a system to measure that in a very precise way. Right?
Anyway, when you have hydrogen, oxygen, CO2, it's a kind of syngas.
Yes, for sure. You're deadly right. Exactly.
Okay. Someone present in the auditorium may have a question if you are. Okay. You can ask in Spanish and I can
Si se quiere
translate.
hablar
You are.
español también no pasa nada. Podemos
Hablo
responder
español también, así que no hay problema.
Poquito, pero hablo. ¿No?
Ok, bueno, si alguien está interesado en contactar al profesor y a la profesora Cristín, pues ahí está con mucho gusto. Así que, bueno, agradecerles a todos ustedes por la presencia, estar acá con nosotros y también a los que estaban conectados vía streaming. Es importante mencionar de que digamos, estos seminarios que hemos estado realizando durante este año están grabados. Por lo tanto, aquellas personas que por X o Y circunstancia no han podido asistir presencialmente, tanto acá en Chile como a nivel internacional, perfectamente pueden acceder al video y pueden ver todos a los participantes que estuvieron acá compartiendo con nosotros. ¿Okay? Así que agradecerles a ustedes. El próximo evento será, Dios mediante, el próximo año. Vamos a tener la visita de colegas de España. Así que esperemos que pues se apruebe todo lo que hemos solicitado y vamos a seguir continuando obviamente en traer a investigadores importantes acá a nuestro país para que nos retroalimenten mucho en lo que están haciendo y que obviamente nos puedan a nosotros ayudar para que podamos hacer investigación que el país necesita, ¿ya? Así que muchas gracias por asistir y que tengan buen resto de día.